Well, thank you for joining this in-depth session where we'll discuss the challenges associated with testing photonic integrated circuits. I know Simon and Stephen and Sophie spent a little time describing this type of technologies, the potential of that technology. So we'll go in depth about that. So joining me today are two experts coming from two different backgrounds. First of all, I have Sebastian Giesmann. So hello, Sebastian. How are you?
Hello, Francois. I'm fine. Thank you very much.
Good. So Sebastian is a product marketing manager at MPI Corporation, responsible for probe systems, product marketing, and specialization on silicon photonics testing, as we'll discuss a little bit later on. Sebastian holds an electrical engineering degree from Dresden University of Applied Science, and he held various positions in R&D, application support, and product management. So that helps a lot, understanding the needs from the lab and manufacturing. But mostly it was, I think, in the semiconductor test industry, but now moving into the silicon photonics. So scheduled also for this talk, I had Lawrence van der Vecht. Lawrence is a subject matter expert based in the US and involved in the PIC technology for probably the past decade now. But Lawrence couldn't make it live to this event, and now we'll hear from virtual Lawrence instead. So at some point we'll have virtual Lawrence giving us some advice on how to test these devices. So myself, I'm François Cougny, product line manager at Exfo, responsible for the line of product being discussed during that session. So don't hesitate to ask questions to Sebastian or myself via the chat on your Teams interface, or you can also use a raise hand if you have a burning question. We'll try to take as many questions as possible during this event. And finally, bear in mind that this session will last for 30 minutes, and then it will be given another time once more in about 30 minutes time. So that way you can attend 2 sessions of your choosing. And to do that, you just refer to the event platform for more information about the other in-depth sessions that you have. This session is recorded and will be available on demand on the platform for months to come. So, so there we go. So let's start with a little interesting statement, I think, from Anders Andrei from Huawei Technology, Sweden. And by the way, he's not the only one making this statement, okay? Data center electricity use is likely to increase about 15-fold by 2030 to 8% of the projected worldwide demand. Okay, so and that projection is also backed up by this article from Nature, where it is indicated that simply scaling up the current technological solutions to address the increase in traffic that we are seeing, the telecom industry as a whole will use up 1/4 of all electricity worldwide, and so you can't continue on this exponential trend. And here it's only 2030, but if you keep going in that way, you'll use up all of the energy by 2050 or so. So the upcoming challenge is huge because within 10 years, or not even 10 years, we need to come up with new solutions for, at least for the telecoms, to be researched, developed, put through production, packaged, and sold. And all that to unprecedented scale, and obviously with as little impact on cost to the end customer as possible. So from at least from a photonics front, we need to have new components that are more efficient, compact, cheaper, more robust even. And so obviously the photonic integrated circuits are help at hand for this development, at least once again on the photonics front. So these PIC are compact devices, compact chips. They can have up to hundreds, even thousands of components or optical functions onto them. And the advantage is that you can have active or passive components, so things that emit light or modify the light. And these can consume as little power as possible, but also they're easier to fabricate because you fabricate them on a wafer. And so the manufacturability is faster, it is better. You can deal with larger volumes at a lower cost. And you can even think about integrating the best of both worlds, the electronics and the photonics part. So here I have the slogan from is derived from Daft Punk. They're French, I know. Smaller, faster, denser, greener, cheaper. This is what we can hope to do with this PIC technology. And this is not just related to telecoms and datacoms or data centers. These key advances are being made in many domains thanks to this PIC. Take LiDAR, for example. You can make LiDAR for autonomous car lighter and cheaper, more compact, and to the cost of what is required for the automotive industry. Medical applications where you could have a lab on a chip that is, inserted into your skin and you just have it checked every now and then. Or quantum computing, quantum photonics, very powerful here at creating very complicated devices on a single chip. So the advantage of the large volume, the reproducibility of the chips also makes it ideal for consumer market usage because you can make millions of these chips. And then once again, the more you make, the lower the cost of these chips is. So in terms of energy efficiency, once again here, we can still have advantages in all these technologies. But, and there is always a but here, is that all is not blue in the sky of PIC. And when it comes to testing, it is quite of a challenge, actually. There are two challenges. One is the alignment process, and Sebastian will touch about it. But also there is a testing part, and there are some challenges associated with this. So let's join now Virtual Lawrence, who will tell us more about what these challenges are. And if you can't hear Virtual Lawrence, let me know, and I will check that he can hear him.
Thanks, Francois. Let me start off by apologizing for not being here in person, caused by unforeseen last hour changes. Not something that I anticipated, but I guess that's the nature of the business. But as Francois mentioned here, looking at slide number 7, PIC technology is quite broad, and it is a technology that can be used for many different type of applications and industries. But no matter the application, the bulk of the cost, as stated on this slide here, can be found in testing the device. And here a conservative number of 30% is mentioned, but again, being conservative here, a more realistic number, or not a number that surprises us, is found around 50 to 70% or even 80% of making the device, which is substantial, of course. So the cost of testing the device is multifaceted, meaning that the tip typically gets tested at every stage of the echo chain. There are 3 stages shown here, but depending on the process that one could follow, it could be there could be more steps in between. So at the design level, and it's typically where the device gets tested as a proof of concept. Then going further through the echo chain is at the foundry, and at the wafer disk level. The next step would be mass production, and once the wafer has been cut into bars and dies, is where it gets tested, and then finally at the point where the chip gets packaged is another stage where the device gets tested. So at each stage in this echo chain, every port on every PIC gets tested multiple times. This to ensure that the measurement results are repeatable and accurate, which is of course one of the testing objectives, which I'm going to touch on in the next slide. And this echo chain is not necessarily followed by just one company, but by multiple companies, which poses another challenge. So to drawing a conclusion on the actual performance of the device requires one to cross-correlate every set of data on every single PIC component for final quality assurance and an actual pass-fail of the device. So there's an enormous amount of data that needs to be processed and cross-correlated just to make sure that whatever is being tested makes sense. So bringing the testing of the PIC into perspective, slide 8 shows really the challenges and objectives, summarizing what most PIC companies are being faced with. So for the sake of keeping the overall testing time to a bare minimum, one should always run a measurement once to come to accurate results. You only want to do it once and not multiple times, which will cost more. So the obvious way to test this is by running multiple measurements to ensure repeatability, but this is something one wouldn't have to done 100 times on the same device to prove once the device's accuracy. Once it's been proven, then it's pretty much carved in stone, and making it repeatable for the other devices on that same disk. So EXFO has a unique method which is based on a Michelson interferometer that assures a wavelength accuracy of plus minus 5 picometers or even lower with the use of an external acetylene gas cell. So part of the accuracy topic is dynamic range, which again makes the EXFO system unique to the market. Francois, I know further down, will explain a few of the products that are being used in this PIC setup. An OPM-based system with one dynamic range setting rules out any possible anomalies caused by out-of-ranging of optical power meters, which is something one could interpret as an issue with the PIC under test. So having a power meter with one clean dynamic range really helps getting a clean and a one-time scan result that makes sense. So the total cost of testing the PIC device being in the order of 30% or more requires defines really the speed of the system. And this is not just the test instrumentation that's being used, but also the alignment, which of course takes time, of the system going in, probing into the PIC and out of the PIC. This alignment process needs to be fast too. So on the instrumentation side, this would mean or would require a fast sweeping laser source or laser sources, depending on what wavelength range or ranges need to be covered. And on the power meter side, it would require a fast data acquisition system, which is also something that EXFO has unique solutions to offer. So not every PIC device is the same, which means that different instrumentation is needed. And depending on what the testing needs of a given PIC device is, would require different instrumentation. So having a modular system or setup would allow one to make hardware modifications and changes as needed without spending a ton of money. So a modular setup, similar to the CTP10, would allow for adding new functionality and functions over time, based how the market evolves and based on what kind of parameters would need to be tested on the PIC under test. Lastly, on this slide, automation plays a very, very big role in addressing the speed and scalability, which is something addressed by the GUI that we have as part of the CTP10 or OSA20 for active device measurements. But also we collaborated with a third-party wafer disk handler system like a manufacturer like MPI and with a software company by the name of EVA, EHVA. And on the automation part, there will be a dedicated test talk addressing just that particular topic. So feel free to sign up for that test talk, which is scheduled for April the 22nd, called test talk number 2. Slide 9 shows the measurement taken on a particular PIC-based Mach-Zehnder modulator, both on the physical performance and traffic, so actual usage performance. The physical performance, as shown on the bottom right, shows how the optical spectrum of a Mach-Zehnder modulator changes based on the different voltage settings applied to the arms of the modulator. So running an optical scan at different voltage settings shows you the different behavior or changes within the Mach-Zehnder modulator. So measuring an optical spectrum, as shown here, would require a tunable laser source and an optical power meter system. Again, something that Francois will go into depth on in the next couple of slides. So axial function or traffic testing requires products like a bit error rate tester to apply a certain bit pattern going through the optical path of the Mach-Zehnder modulator, and having a product like an optical scope or eye analyzer at the other hand to look at the cleanness of the eye diagram. Again, also here, Francois will be spending a few words on the instrumentation that Expo offers addressing these measurements. So this brings me to my last slide, which showcases a fully automated turnkey photonic integrated test system with optical instrumentation from Expo, wafer disk technology by our collaborator Hewlett-Packard Enterprises, and the actual wafer disk handler system by MPI. That concludes it for me. Thank you, and hereby back to Francois. Thank you.
Okay, well, thank you, Virtual Laurent. Sebastian, we can clearly see on this slide here the setup for the probe station, which is one of the key piece of equipment that you require to couple light into the device for the wafer level PIC testing. Maybe you can tell us a little bit more about this?
Correct. Thank you very much. What we see here is a very typical setup on a 300mm probe station. And as Lorenz already mentioned, this was done in a project where we collaborated with Expo for the measurement part and Hewlett-Packard Enterprises, which provided the devices to be tested. And we actually did everything around the positioning, so the core competence of our probe station company. So as I already mentioned, that's a 300mm system. It's a semi-automatic system. That means we will load the wafer manually, and then we can automatically step through a wafer, align the fibers, and test the full wafer automatically. This setup is also available in a 200mm version, so for smaller wafers, and is also available with an additional loading option. Then in this case, we would have a fully automated system where the wafers can be loaded onto the chuck automatically. We see here in the center, there are two positioners. In this case, we have two hexapod positioners. This is the most advanced and most flexible solution. It is recommended for everything where we need to adjust angles, which is especially the case for testing with fiber arrays, where we need to overcome the fiber array misalignment to the device. There are also more simple solutions available, where we have, for instance, instead of the hexapod, we have just a motorized X, Y, Z positioner, which does the coarse positioning. Then yes, this is a pure optical to optical setup where we see in the back here the laser sources and the optical power meter from Expo. This was the requirement in this case for this device. It's certainly possible to do also a combination with electrical measurements. In this case, we just need additional positioners for instance, RF or DC applications. On the two screens here, we see One, or the lower screen is for operating the probe station. This is required during the setup. And for the automation, we can completely remote control the probe station and also the measurement instruments. On the upper screen, the results are displayed. In this case here, we're doing a IL measurement sweep, and we step from device to device. So to automate this, we have the ability to do this, like in this case here, with Python scripts. But we also came up with a nice solution with a test executive, where we also collaborate with partners. And this test executive is now available to do this kind of measurements in the optical setup. And it's called Measumatic. So this is available now. On the next slide, we actually recorded a video to show how such setup is done. So this is a video provided from Expo, where we put everything together, what has been done. It starts with a nice sentence from Ashkan. I can design and manufacture any PIC device I like, but testing is costly and time consuming. So this is very true, and Lawrence has already talked about this in more detail. So what we have done here is first we see an overview of the probe station. So that's exactly the setup we have done. It's a 300 millimeter probe station where we have the laser source and the optical power meter here in the back connected to the fibers. The wafer is loaded onto the chuck, in this case manually. And then we see here the fibers in more detail. So there are two fiber holders. And now we are stepping through the device. So same setup here with the upper screen for the measurements. Here we see the stepping of the wafer, how the fibers are scanning each side. And then we see it here in the microscope view for the input and the output fiber. And the light intensity is recorded at all time because we want the maximum during the alignment, the light intensity. So this would be the X4 measurement screen where we do the wavelength sweep. And this is a typical result for the measurement, for the IL measurement in this case. And then the stepping is done with the individual fibers in the device. This is when the positioner moves. There's another fine alignment done, and then we can do the next measurement. And the next measurement then is also collected with the X4 measurement system. So here we saw a stepping to the next device. This is when the wafer moves, and then the curve here gets overlaid. We can zoom in, we can analyze here, so and look at the two different devices. That's already the video. Thank you, Francois.
Okay, well, thank you very much, Sebastian. It's interesting to see that even just simply coupling the light in and out of these components on the wafer requires really specialist equipment, and that's why it's important to work together to find solutions, because we need specialists in each of these areas. And as mentioned by Lawrence earlier on, Expo also offers a range of test instrumentation geared for PIC testing. So really keeping speed and accuracy in mind at all time. And we have discussed quite extensively about the passive optical component tester, so things that are going to transform light but not necessarily emit light, with the CTP10. That we have seen in the video, but we can also run some tests on devices that emit the light. And in that case, you would require an optical spectrum analyzer, such as the OSA20, that can scan up to 2000 nanometers per second, which means that you can have many scans per second. For alignment purposes and even for testing, it is one of the fastest OSAs on the market today. But going even further with that, you can, on the wafer, perform some functional testing, such as eye diagram with a sampling scope or bit array testing. And in that case, Expo has made the acquisition of InOptical, and InOpticals is specialized in these type of instrument with a BA4000, EA4000, once again keeping speed and accuracy and quality of measurement in mind. So these complete the proposition for a PIC testing solution at Expo. And so I hope that we gave you a glimpse of the challenges and the solutions that we face when testing PIC. So on that, I will thank you again, Sebastian, for joining.
Welcome.
And thank you for attending. And right now, if you want to jump to another session for the second part, or if you want to stay for exactly the same, you're welcome as well. All right, take care and goodbye.
Thank you. Bye-bye.